So one of the most important concepts in algebraic geometry is the morphisms. Morphisms between algebraic sets. Now we have already defined what algebraic sets are. So for this case, we will fix two algebraic sets, say A and B, and then describe what morphisms are. So let us write this down. So we are going to describe morphisms between algebraic sets, which we will denote by phi, and we have two algebraic sets A and B. Now A is a subset of Kn. Notice that K is closed, and B is a subset of Km. Again, K is closed here. Now immediately we need to associate the ring of regular functions with it. So we know A is algebraic set, so now we write down the ring of regular functions associated with it. Now since it is Kn, we have n variables, and similarly for O of B we will have m variables because it is Km. Now we want to characterize the polynomials which lie in this ring. So say they are polynomials f which lie in the ring OA. Now what happens when f acts on A? Now when f acts on A, you land in K. Obviously if you are in I of A, you get 0. If you are not in ideal of A, then you get some element of the closed field K. Yeah, so this is important to know. Similarly with O of B, it is a subset of Km. So we have y1, y2, y3 all the way to ym over ideals of B. Similarly, we will characterize the functions of this ring. These functions, say G, act on the set B and take it to the field K. Obviously, if the function G lies in the ideal of B, it will map to 0. If it does not lie in the ideal of B, you're just evaluating it at certain points basically. So B consists of m points, you evaluate the polynomial at those points and you end up with the element of K. Just a polynomial in m variables evaluated at those m points. You're given values of y1 to ym and you just plug in and you get a value in K. That is what it means. So what is phi? Phi is a tuple f1 to f2 to fm, yeah, where each fi lies in O of A. So each fi lies in O of A. So each fi is a polynomial which lies in O of A. Now each polynomial lies in O of A, you evaluate it on the set A, you get corresponding AI, which is the field. So f1, you plug in Kn, you get A1, f2, you plug in Kn, you get A2, and fm, you plug in Kn, you get Am. So you get the tuple. So phi is nothing but a tuple. Now consider this function G acting on the algebraic set B. Now G is part of OB, as we have seen the characterization. G will take B to K. Now notice the composition of this map. Yeah, you first apply phi and then you apply G. You get a map from A to K. Now obviously map from A to K is nothing but lying in the ring OA. Yeah, so you get OA. Okay, now we want to collect everything which we have said. So you have a morphism from A to B. Morphism phi is given by a tuple of polynomials f1 to fm. Obviously f1, f2, f3, fm matches m with km there. Yeah, so if it was km2, then we will have f1, f2 to fm2. Correspondingly, you get a map between the corresponding ring of regular functions, where G in O of B is carried to G naught phi. So this map you say is phi star. Now obviously you define phi star so that G is carried to G naught phi. Notice the contravariance. We had a morphism given from algebraic set A to B, and corresponding to that morphism we have constructed a ring map from OB to OA. But obviously given any map in OBG, you carry it to G naught phi in O of A. So notice contravariance means the arrows are going in opposite directions. So you have constructed the first bridge. algebraic sets A to B and correspondingly ring maps in the opposite direction. So the first example, so this is just repeating what we have said before. Characterization of a element or a polynomial in O of A, it takes kn to k. Yeah, you plug in values for x1 to xn and evaluate the polynomial f at x1 to xn. Second is bijections. Obviously kn to kn, these are all polynomials of degree 1. Another example we give will be of projections. Yeah, so number 3 example will be projections. I'll just write it down. This is very simple. You just project onto certain number of elements. Now just a quick recap. You're given a morphism phi from algebraic set A to algebraic set B. This morphism is given in terms of a tuple of polynomials of O of A. And then given this morphism, you can take any element G of O of B to an element of O of A. So we now want to record some more examples. Say, consider this vanishing set of the parabola, and this is a subset of K2. Yeah, obviously parabola is a subset of K2. And then we draw a map from K2 to K, and where K is the x-axis. So we write down the equations. So x-axis is nothing but y equals to 0. And so what is a morphism? So we have morphism from vanishing set of the parabola. So our algebraic set is what we have drawn on the left side, and this is nothing but a projection map. Say we call this phi 1. So this is a subset of K2, the top part, and the bottom part x is equal to K. Okay, so let us make this clear. Now we can draw an inverse map from K to K square. So T or K to K2. Obviously if you put x as T, then y is equal to x square. So that will be T square. So this is map phi 2. This goes from K to a subset of K2. Okay, so now phi 1 and phi 2 are inverses to each other. Okay, now another example. This example is important and is there in almost every book on algebraic geometry. So we have a morphism from this, on the left side we have a line, and on the right side we have the vanishing set of y square minus x cube. So let me write down in the top part also, this xy was the vanishing set of the parabola. Yeah, so this was our algebraic set. So now in this case we have algebraic set as this, and which is in terms of figure it is y square equal to x cube, and we are taking K, that is the entire line, to subset of K2, yeah, which is given by the vanishing set of y square minus x cube, and we put the morphism as phi 1. So you take T, so if you put x cube as T square, then T square cube is T6, and therefore y will be T cube, because T cube square will again be T6, and that's how you will get the equality. So this is a morphism. Yeah, so you see there we have given two polynomials, T square and T cube. In the top part we had T and T square. So we have to show later, very importantly, that there is no inverse morphism. Now in part 4 you see there is an inverse morphism. Yeah, you have phi 1 and you have an inverse morphism phi 2. And later we will show there is no inverse morphism in terms of polynomials. So this map does not have an inverse morphism in terms of polynomials. Okay, so this is important and we will show later. But we do have a set theoretic bijection, because we can define a set theoretic inverse of the map phi 1. Although we cannot define it in terms of polynomials, but we can still have an inverse. You could have guessed it by now. It is nothing but t cube over t square for t naught equals to 0, and for 0, 0 gets mapped to 0. Now the map above and the map this below, they are inverse to each other. So you do have a set theoretic bijection between the line and this graph of y square equals to x cube, or the vanishing set of y square equals to x cube. So we do have a set theoretic bijection. But you see, this is not a polynomial, and we will later show that there is no polynomial inverse. On this slide, we want to characterize the map phi star, which goes in the opposite direction to map phi. So map phi takes algebraic set A to algebraic set B, and map phi star takes the corresponding rings O of B to O of A. So this is what we have covered till now. But what is this map phi star? Phi we already showed in terms of polynomials, and in this slide we characterize phi star. So just writing down the definitions of how we characterized it. So let us give some examples, and then we will give the general form. So this is just examples copied from the previous slide. So we have vanishing set of the parabola mapping onto the x-axis. So this map phi, obviously the elements, so we have the set A and B. Yeah, so the elements of the vanishing set y minus x square are of the form x, y, x comma y, where x is say t and y is obviously then t square. Yeah, so we have x and y here, say x comma y, elements of K2 getting projected onto x, just like in previous slide. So let us write this down. So you have xy projecting onto x, and the map phi just takes the first variable, and the first variable is t. Yeah, so it just takes t. Phi is just the t. Okay, now this is important. So t is the polynomial. So phi, you know, it's characterized in terms of polynomials. So t is the polynomial acting on the set A. So the phi star map is in the opposite direction. Yeah. So the ring map OB is of this form, and ring map OA is of this form. Yeah, KT you could have written KA or KM or KX, anything. So what does T map to? So this T maps precisely to the component it came from. So T maps to what it came from. It came from X. So that is what it will map to. Okay, this example, we will cover another example. So this is example again from the previous slide, example 5. So in this case, we have map from K to K2. Yeah, A is equal to K and B is subset of K2. So again, in the first example, it is very clear. X gets mapped to T, and we are taking the map in the, taking the same map. So now we focus on this example. So y square minus x cube. Again, you know the polynomial phi. Phi consists of a tuple of polynomials. In case 1, there was just one thing, t. In this case, we have two polynomials, t square and t cube. Yeah, so elements of algebraic set A are taken to t square and t cube. Okay, now what is the corresponding ring map which we need to characterize on this slide? Now O of A we just write as kt. Obviously it is just k, so you could have written kx, km, k, whatever. Yeah. On the right hand side we will have this, it is a subset of k2, so it is kx comma y modulo the ideal generated by y square minus x cube. So let x bar and y bar be the image in this map. So x bar is image of x and y bar is image of y in O of p. Obviously because it is kxy modulo the ideal, so x modulo the ideal will be x bar, y modulo the ideal will be y bar, and that is precisely, it gets mapped to, x bar gets mapped to the first component, y bar gets mapped to the second component. Yeah, so what is it in general? So again, just write it down. This map phi is a collection of tuple of polynomials. So you have these m polynomials, phi 1 to phi m. You have the corresponding ring maps now. Yeah, so the corresponding ring maps, first you write down the ring. Obviously this will be k, there should be m variables, k x1, x2, x3, x4 all the way to xm modulo the ideal. Now once you modulo out the ideal, you have to take the image of x1 modulo ideal of b, which will be x1 bar, x2 modulo ideal of b will be x2 bar. Now similarly for OA you have this map I of A. Yeah, you notice that this phi 1, phi 2, phi 3, phi 4 all the way to phi m, these are all elements of O of A by definition. Now in O of B you take x1 bar, which is image of xi modulo I of B, x2 bar which is x2 modulo I of B. So x1 bar gets mapped to phi of 1, just like x bar got mapped to t square in the previous example and y bar got mapped to t cube. Similarly we have this, and each of these phi 1, phi 2 and phi m are anyway elements of O of A by definition, and they are polynomials in the ring O of A. And that was the definition. So this is how the characterization of phi star is. So on this slide we construct the very important bridge, or show the equivalence of two bridges. One is morphism between algebraic sets, and morphism between algebraic sets is nothing but geometry, as we have seen, going from parabola to a line, and then we have the corresponding rings. So A to B is the geometry, correspondence between figures. On the left side and on the right side we have morphism between rings. So we have a functor f which takes us from algebraic sets and their morphisms to rings and ring homomorphisms. So this functor f is fully faithful, and this proposition we want to prove. So this functor f is fully faithful. So on the left side we have morphisms, and on the right side we have homomorphisms between rings. So now you can see why it is called algebra and geometry. So on the left side we have geometry, correspondence and figures, and on the right side we have algebra, and that's why the name is algebraic geometry. So very important corollary. So if we have iso from A to B, then we have iso in the corresponding rings also. So if and only if the opposite arrow, the contravariant arrow from ring of regular functions OB to OA, so this homomorphism phi star, this ring homomorphism phi star is also an iso. So this is the corollary to the proposition, principally because the functor f is fully faithful. Now the proof. So we have to prove injectivity and surjectivity. So fully faithful means it just takes all the maps in one category faithfully to the maps in the other category. That is, maps have one-to-one correspondence. So injectivity. Now if there are two morphisms between algebraic sets A and B, both of them are equal, then the ring homomorphisms are also equal. Now why are they equal? You know the ring homomorphisms from the previous slide are precisely characterized by the morphism itself. Yeah, the morphism has pieces phi 1, phi 2, phi 3 all the way to phi m, and you know the ring homomorphism, when you took ring homomorphism is x1 bar going to phi 1, x2 bar going to phi 2. So it is precisely characterized by the morphism, and therefore if the two morphisms are equal, the polynomials are equal, and therefore the ring homomorphisms are equal. This is construction precisely from the previous slide. Now we have to show surjectivity. So if you have a map here, say a ring homomorphism H, yeah, so say B is of dimension n. So let us write this clearly. This will also help us to understand what I was trying to say. Yeah, so you had xm, because B is a subset of km, modulo ideal of B. On the right hand side we have, say A is subset of kn, so we have to have n variables now. So y1, y2, y3, y4 all the way to yn, modulo ideal of A. So x1 bar, which is image of x1 modulo IB, this goes to phi 1, x2 bar goes to phi 2, x3 bar goes to phi 3, xm bar goes to phi m. So this was the corresponding morphism phi, and that's why we have case 1. Yeah, so now we have to show, if you have such a ring homomorphism, we have a morphism phi, which I've just written down from phi 1 all the way to phi m. So to show surjectivity, we have to show that this morphism phi, which I've just written down from phi 1 all the way to phi m, which is so image of phi, is contained in B. Yeah, so you took a map H, which is characterized by x1 bar going to phi 1, x2 bar going to phi 2, xm bar going to phi m. That tuple 1 to m makes phi, and we are saying corresponding to map H, we have this map phi. I've clearly labeled how map H is defined. So basically we will have to show this. Say a polynomial f, x1, x2, all the way to xm lies in ideal of B. Now you take that polynomial, you evaluate it at phi 1, phi 2, phi 3, phi m, evaluate it at point x. Now x is a point in A. So if you have to show image of phi is in B, you take a polynomial in ideal of B. So that polynomial is now evaluated at phi 1, phi 2, phi 3 all the way to phi m at a point x lying in the algebraic set A. So if it lies in the image of B, then this has to vanish on B. So let me write down this again. So you have taken this polynomial f x1, x2 all the way to xm in ideal of B, and you want to show, if you replace x1 by phi 1, x2 by phi 2, phi m by xm by phi m, and evaluate it at a point x of A, you get 0. So what is this f of phi 1, phi 2, phi m? Now we're just going to write down what we have written on the left hand side. So I'm replacing phi1 by h of x1 bar, phi2 by h of x2 bar, just precisely what the figure is. Now you have a polynomial, you can take this homomorphism outside, and this is what we get. Now notice that x1 bar is an image of x1, x2 bar is an image of x2 modulo I of p, xm bar is xm modulo I of p. But the polynomial originally f x1 comma x2 comma xm, this originally lies in ideal of p. So what we have now here is image modulo ideal of p. So it has to be 0. Yeah, because it lied in ideal of p, you modulo it out by ideal of p, you have to get 0. So let me write this clearly. This is nothing but image of this thing in O of p. But f x1 comma x2 all the way to xm lies in the ideal of p. So this vanishes in OB, and therefore it is 0 on the set B. And that is the end of the story. A few slides ago, we had mentioned that there is no bijective morphism from K to vanishing set of y square equals to x cube. So we will prove that here. So if there is an iso, we will have a ring isomorphism. Yeah, so you have the ring corresponding to y square equals to x cube and ring corresponding to K, which was kt. Yeah, so this kt is a unique factorization domain. This we know because K is a closed field. But this ring OB is not a unique factorization domain, and we will use Eisenstein criteria to show this. If you do not know Eisenstein criteria, just Google it right now. So look at this factor y times y plus 2x. Yeah, this is irreducible because both y and y plus 2x are linear. You expand it, replace y square by x cube because the ideal you modulo out is y square minus x cube equals to 0. So y square is equal to x cube. Now you factor x out, and I'm saying that x square plus 2y is irreducible. Now this is irreducible by Eisenstein criterion. You consider x square plus 2y as a polynomial in x and 2y as a constant, and you use the prime 2. And thus we have shown that one ring is UFD and another is not.